Recently, I've been wondering, what time is it on Mercury? It turns out the answer is a little more complicated than you might think. Let's imagine two perfectly accurate clocks, one on the geoid surface of Mercury and the other at mean sea level on Earth. The clocks are synchronized at the beginning of the current Julian period, 12 p.m. on January 1st, 4713 BC. Every day, when our Earth clock says 12 p.m., we look in our telescope and record the time we see on Mercury, taking into account the time it takes for light to travel between the planets. If we draw a plot with the current day on the x-axis and the time we read from our Mercury clock on the y-axis, you would think you would just see noon on both clocks forever. But that's not actually what happens. The value on Mercury's clock is changing. Time is a funny thing. It works differently depending on where you're standing and what you're looking at. So, from our perspective on Earth, the clock on Mercury is running just a little bit slower. What's even more mind-bending is we can plot the length of a second on Mercury at any point and see that the length is changing over time. By the end of this video, you'll know what time it is on Mercury now, and you'll understand why it's different in the first place. For now, we'll move our Mercury clock to the corner and speed it up a bit. We'll check in again at the end of the video. The rest of this video is divided into a few parts. First, I'll talk a bit about timekeeping and chronology, explaining time standards, the Julian period, and Pope Gregory XIII's fraught relationship with the month of October. After that, I'll walk you through the basics behind relativity that hopefully make it easier to understand even if it's been a while since you took a math or physics class. Finally, I'll walk through the steps I took to apply these theories to the actual positions of Earth and Mercury in code, and we'll get to see how much time Mercury has actually lost over the last few thousand years. I think the explanations are what make this question interesting in the first place, but if you really want to skip to the end and just find out what time we get, here's a list of insightful comments you can leave to pretend you watched the whole thing, and here's the timestamp you can skip to. Alright, good. Now I can give you way more information than you ever knew you wanted about calendars and time standards. I'll start by explaining why we're starting our clock at the beginning of what's called the Julian period. The need for the Julian period comes from a discrepancy between the modern Gregorian calendar and the Julian calendar that preceded it. As the name suggests, the Julian calendar was established by Julius Caesar around 45 BC. There were some mistakes in its implementation that were worked out over the next 50 years or so, but essentially the calendar assumed that years were exactly 365.25 days long, and added a leap day at the end of every fourth year to keep the dates aligned with the movements of the sun and stars. Unfortunately, this number isn't quite right. The actual value varies over time, but currently averages out to about 365.2422 days a year, which means that the calendar shifts relative to the position of the sun by a rate of about a day every 129 years. It's likely that the designers knew the calendar wasn't quite right, but weren't particularly concerned about it. As it turned out, the Catholic Church would prove to be much more concerned. Among other things, the First Council of Nicaea, held in 325 AD, decreed that all Christians should celebrate Easter on the same day, but did not actually specify how this was to be done. After another 500 years of debate, thankfully, most Christians agreed on a really simple method for determining the day of Easter. It should obviously be held on the first Sunday after the first full moon after the vernal equinox. As easy as that sounds, there were a few problems. Chief among them is that the vernal equinox had been defined by the First Council of Nicaea as the 21st of March back in 325 AD. But by the 8th century, when many people were agreeing about when to celebrate Easter, they were already basing their calculations off of a vernal equinox that was off by several days. By the time of the Gregorian reforms, the equinox fell a full 10 days earlier than the church definition suggested. To realign the calendars, it was decreed that October 5th through October 14th would be skipped that year, though adoption actually took place in different places at different times. The new calendar has a more complex set of rules for determining leap years, which means that it will only drift by about a day every 3,000 to 7,000 years. It certainly makes things easier moving forward, but having random days cut out of the calendar at different times and different places is a nightmare for historians and astronomers. This is where the Julian period comes in. Each Julian period begins and ends with the convergence of three immutable cycles: the 28-year solar cycle, the 19-year Metonic lunar cycle, and the 15-year Roman text reassessment schedule. The tax schedule seems like an unreliable, if not silly, inclusion, but Joseph Justus Scaliger, who came up with the idea of the Julian period, had his reasons. Scaliger's magnum opus, De Emendatione Temporum, attempted to create a comprehensive chronology of historical events, and the sun, moon, and taxes were all common reference points cited by the historical sources he used to compile the chronology. The tax cycle inclusion certainly shows a bias towards classical Roman and Greek histories, but to his credit, Scaliger was also one of the first chronologers to make serious use of Persian, Babylonian, Jewish, and Egyptian records in his work. Of course, I'm oversimplifying, so here are some papers you can cite if you want to grill me in the comments. The last time these cycles all began in the same year was January 1st, 4713 BC, which we chose as our reference time at the beginning of the video. This is a reference date that astronomers can use to count the Julian day, which is the number of days that have passed since the start of the Julian period. At the time of this video's release, the Julian day count is just over 2.4 million, and the next period will begin 7,980 years after it started, when the cycles converge again in the year 3268. There's also the entirely separate issue of time standards. I'm not talking about time zones. Those are all based on one time standard, Coordinated Universal Time, or UTC, not to be confused with UT0, UT1, UT2, or UT1R, just to name a few. You've probably heard of atomic clocks that use atomic transitions like those in cesium-133. International Atomic Time is based on data from over 450 clocks spread across the planet. Turns out, these clocks are more accurate at keeping time than Earth is. Over time, Earth has minor variations in the speed of its rotation because, nobody's perfect. To keep UTC aligned with solar time, leap seconds are occasionally added or taken away from the standard, though by 2035 that practice might end, letting UTC slowly drift out of sync with the sun. And that is just scratching the surface. I spent an embarrassing amount of time on Wikipedia sorting out the differences between geocentric coordinate time, barycentric coordinate time, terrestrial time, solar time, ephemeris time, and what on earth I was doing with my time. The short version is that terrestrial time is an idealized reference for clocks on Earth's surface that's free of time jumps, perfect for astronomy. It has a fixed offset from atomic time of 32.184 seconds for continuity with an older standard, and we can convert atomic time to UTC by adding in the leap seconds that account for inconsistencies in the Earth's rotation. I used terrestrial time and Julian days for all of my calculations, and then translated the final results into UTC dates on the Gregorian calendar. Now that we've worked out our time coordinates, we can walk through some simple examples to understand the basics of relativity, and why we know that our clock on Mercury is falling farther and farther behind. One of the key components for understanding relativity is what we call a reference frame. Imagine that you're standing at some point on Earth where there are three rigid rods with distance markings all at 90 degrees to each other that we can use to measure things around us. We might look across the street and use our rods to say, those trees are 2 meters apart. If we're standing there with a stopwatch, we can measure the position of something moving at different times. For example, that sentient banana is moving at 2 meters per second. The stopwatch and the rods constitute a reference frame, a way to measure events based on where you are and how you're moving. Of course, you might realize that a banana who's capable of considering the nature of selfhood is not something you see every day, so you would probably hop on your bike and try and catch up with it. We could continue to describe our position in terms of the original reference frame, but now that you're moving at the same speed as the banana, it's probably easier if you just choose a new reference frame that moves along with the bike. In this frame, you and the banana appear to be stationary since the distance between you is not changing. Now that we have two different reference frames, we might want to convert coordinates from one to the other. We can try to come up with some simple rules based on how reality works in our experience that will help us determine how to compare measurements across reference frames. For example, it seems pretty reasonable to assume that the distance between 2 points on a rigid object is independent of the chosen reference frame. That is to say, if you were to measure the distance between the trees, the values would be the same whether you're standing at the origin of the original frame or racing down the road in pursuit of a supersized fruit grappling with its own mortality. Similarly, lived experience seems to suggest a second analogous proposition, that the time between two events is independent of the chosen reference frame. Since it seems safe to assume that the banana ironically slipping on a discarded t-shirt happens at a definite point in time, independent of whether you're moving or a stationary observer. The third proposition is that the laws of physics work the same way in all reference frames, or put simply, the rules are the same everywhere. We call this the principle of relativity. And finally, a proposition that doesn't seem obvious, but which you've likely heard before, the speed of light in vacuum is constant. More specifically, the speed of light in vacuum is constant in all reference frames. This may not sound particularly controversial, but it comes with some complex implications that will force us to revisit our other assumptions, so it's worth discussing a few early experiments that support this claim. The first conclusive validation that light travels at a finite speed that I'm aware of comes from observations made by Ole Romer in 1675. You can see the basic components of his observations in this figure, published in 1677. Romer took a number of observations of Jupiter's moon Io, which orbits the planet every 42.5 hours. Every time it orbits, there's a brief period where it disappears behind Jupiter. Over many observations, Romer noticed a discrepancy. Let's imagine the Earth is at position L when Io comes out from behind Jupiter at point D. Io orbits Jupiter every 42.5 hours, so 42.5 hours after it first appears at point D, it should return to appear there again. In that same period, Earth has moved from point L to point K. If light doesn't travel instantaneously, it would need to travel the additional distance from L to K before it is observed on Earth. The opposite would be true on the other side. We can imagine Earth starting at point F when Io first appears or disappears, and being at point G when it returns to the same position again. That's exactly what Romer observed. The difference in time was hard to measure precisely over the period of one orbit of Io, but when Romer compared the time it took for 40 transits when the Earth moved away from Jupiter versus the 40 while Earth moved towards Jupiter, the difference was readily apparent. Armed with this information, he appeared before the Royal Academy and successfully predicted that Io would appear in the Paris sky 10 minutes later than existing tables predicted on the 9th of November. This marked the first of a series of experiments demonstrating that light did not travel instantaneously, but had a finite speed. But how do we know that light really does travel at a constant speed in all reference frames? While a number of experiments and observations have demonstrated this, one easy to visualize example comes from work on binary stars by Willem de Sitter in 1913. De Sitter imagined what would happen if a star's velocity was added to the velocity of the light it produced. If that were the case, light released while the star moved away from us would travel slower than light released when it was moving towards us. Over cosmic distances, he predicted the fast light would overtake the slow light, distorting our measurements from Earth. But we didn't observe any of these odd patterns when observing known binary star pairs. De Sitter determined that an upper limit of 0.2% of the star's velocity could have been passed on to the light, an upper bound that is shrunk by orders of magnitude with later experiments. The existence of a constant speed of light has immediate and deeply strange implications. Let's return to our sentient banana. It's nighttime now, and as it walks towards you, you realize it glows, and it emits a pulse of light when it's exactly 2 meters away from you. From your reference frame, the light travels 2 meters at the speed of light c. The time it takes is the distance divided by the speed, about 6.7 nanoseconds. Just like the star, it doesn't matter that the banana is moving. The light's speed is constant. But let's attempt to bridge the intersubjective chasm and imagine the situation from the perspective of the banana. In their reference frame, you are moving towards them. When it emits a pulse of light, the light travels at the same speed c towards you, but while the light is in transit, you close some of that distance. This means the light has less than 2 meters to travel to reach you. So from the banana's reference frame, the light arrives in slightly less time. If we wait that amount of time, the light would overshoot you by the distance the banana has traveled in that time. Our initial set of propositions have taken us to a paradox. We have two observers, both of whom correctly measure the speed of light to be c. Yet when they calculate the time for the same event, they arrive at different answers. To resolve this paradox, we can use some simple math to come up with a theory and then see if it holds up experimentally. Here we'll use a classic thought experiment, a light clock. Imagine two mirrors A and B facing each other. At mirror A, a light pulse is emitted. It travels to mirror B, reflects, and returns to A. Each round trip is one tick of our clock. If the clock is stationary, the distance the light travels is simply up and down, twice the height between the mirrors, which we'll call h. The total distance is 2h. Since distance equals speed times time, we can say that 2h equals c times delta t, where delta t is the time for one tick. Now, what if this clock is moving past us at a high velocity? You could even imagine that this clock was placed on Mercury, and that you were watching it from Earth as it passes through the lens of your telescope. From our perspective, the clock is moving sideways. As the light pulse travels from mirror A to B, it must travel along a longer diagonal path and follow a similar path back to A. Since the light travels a longer distance at the same speed, this means it must take more time. Let's call the time for one tick from our moving perspective delta t prime. We can use what we know to define the length of each side. The vertical side of the triangle is the clock's height, h. The horizontal side is the distance the clock moves in this half of a tick, its velocity v multiplied by the time, delta t prime over 2. The hypotenuse is the actual distance the light travels. This is the speed of light, c, multiplied by that same time, delta t prime over 2. To calculate how much more time this takes, we can use the Pythagorean theorem. The hypotenuse squared equals the sum of the squares of the other two sides. We substitute our values to get the starting equation. Our goal is to find the relationship between delta t, the stationary clock's time, and delta t prime, the observed time when the clock is moving relative to us. To do that, we can substitute h. From our stationary clock, we know that h equals c times delta t over 2, so let's plug that into the equation. From here, we can just do a bit of algebra to get delta t prime in terms of delta t. We distribute the squares, clear the denominator, shuffle around the terms, factor out delta t prime, divide to isolate the term, factor out and cancel c squared, take the square root, and end up with delta t prime in terms of delta t. If we think back to what these variables represent, we can infer that if we observe this clock on Mercury from Earth, we see the same time we measure, delta t prime, is equal to the time measured by an observer on Mercury, delta t, divided by a term that depends on the clock's velocity. Since this denominator is always less than 1, assuming relative velocity is the only thing we have to take into account, the time on Mercury, as measured from Earth, will always be longer. Or another way to think about it, if we set up a stationary light clock on Earth with the same distance between its mirrors as a clock on Mercury, for every full tick we observe on Earth, we see slightly less than one tick on Mercury. If you're curious about the large number of details I've glossed over, as well as the effect of this constant speed of light on distance, you might want to look up the Lorentz transform. Revisiting our initial propositions, we're forced to a startling conclusion. Accepting the constant speed of light means we must discard our first two assumptions. Neither time nor distance is absolute. They're relative. But we still get to hold on to the principle of relativity. The laws of physics are still the same everywhere, even as the Earth rotates and the solar system hurtles through space. Except what we've talked about so far is only part of the story of relativity, the special case where the velocity of the reference frame is constant. Mercury has velocity relative to Earth as it orbits the Sun at each point in time, but that velocity is constantly changing due to the solar gravity that keeps it in orbit. Our light clock calculations don't take the impact of acceleration into account. Thankfully, 10 years after his initial paper on special relativity, and armed with the contributions of a number of contemporary mathematicians, Einstein presented a general theory of relativity that addressed these limitations. The math for this one is a bit more involved, but we can use a simple example to understand the basic idea. Let's imagine an astronaut floating in a box somewhere in the universe. Because the astronaut is floating, we conclude that the box and the astronaut are not moving relative to one another, and that there is no net gravitational force causing the astronaut to fall to a certain side of the box. Looking out of the box, the astronaut can see some asteroids floating past. Since they're moving horizontally, we know that the astronaut and the asteroids have the same vertical velocity. If the astronaut had an upwards vertical velocity relative to the asteroids, they would instead appear to be moving downwards along a sloped path. If, rather than having a constant velocity, the box starts accelerating upwards, two things happen. First, the astronaut is pulled down to what they perceive as the floor of the box, with a force equal to the rate of acceleration. And second, the paths of the asteroids appear to curve from horizontal as the box accelerates. We can also consider what we would see if the box isn't accelerating, but there's a planet underneath the box, just out of view. The gravity of the planet would pull the astronaut to the floor, like before, and that same gravity would alter the path of the asteroids. If they're close enough, they might get into orbit or eventually crash into the planet, but from the astronaut's perspective, the path of the asteroids just curves. In fact, if the astronaut can't see the planet, they won't be able to determine if the force is coming from the box accelerating or from some gravity force beneath them. Einstein goes so far as to say that in both cases we can refer to either of these forces as a gravitational force. Now, let's consider the accelerating box and imagine that both the box and the asteroids are moving much faster. In fact, let's imagine that those asteroids are actually just beams of light. If the box is moving fast enough, those beams of light will appear to curve downwards from the astronaut's perspective, just like the asteroids did. Using a similar thought experiment, Einstein posited that whether the box is accelerating or just under the influence of gravity, the curvature of the light would be the same. This leads to his claim that in general, rays of light are propagated curvilinearly in gravitational fields. What are the consequences of this? Well, we've already shown that the path that light travels is inescapably connected to the way that we interpret and observe the passage of time. What general relativity establishes mathematically is that in the presence of gravity or acceleration, we can't rely on our rigid coordinate system with set distances and times between points. Gravity bends the path of light, but because light always moves at the same speed, it means it's actually bending distance and time to make up the difference, just like we saw with our light clock. Limitations on the telescopes in Einstein's time meant that proving that gravity curves the path of light required measuring the small displacement of about 1.7 arcseconds of light rays grazing the sun, which could only be observed during a total solar eclipse. This displacement was confirmed on the 29th of May, 1919, though recent images from modern telescopes capture much more dramatic examples. If you look closely at this two-scale visualization of the orbit of Mercury, you may notice that the orbit is slightly elliptical rather than circular. We can see that over the course of its orbit, its distance from the Sun is changing. If we compare what the orbit looks like in 1000 and 4000 BC, we observe a slow rotation or precession of the orbit itself. This is predicted by Newtonian mechanics, but those predictions slowly drift away from actual observations over time. In an effort to explain this, some suggested the source of this inconsistency could be an unobserved planet in the inner solar system called Vulcan. But we weren't missing a planet, we were missing a term in our equations. In Newtonian mechanics, we can write out Mercury's potential energy using two terms, one that accounts for gravity and one for the centrifugal force that appears in certain frames of reference, which we can think of as the outward force you feel when spinning on a merry-go-round. But in general relativity, gravity is actually the curvature of space-time. For an orbit like Mercury's, the effect of this curvature can be approximated as an extra term in our potential energy equation. This term slightly modifies our estimated rate of precession for Mercury, adding 43 arcseconds per century. Applied specifically to the perihelion precession calculation, this updated understanding of gravity yields a precession that better aligns our predictions with our observations. Now that we know why these clocks run different, we're ready to run the numbers and find out just how much time Mercury has lost over this Julian period. As a first step, I had to get data on the historical positions and velocities of Earth, Mercury, and the Sun. Thankfully, NASA's Jet Propulsion Lab has created a system called the Horizons Online Ephemera System, which you can programmatically access to get positions for all sorts of objects in the solar system. I wrote a bit of code to fetch and parse position and velocity data at 12 p.m. terrestrial time every day. We can use this data to work out the approximate impact that relativity has on how fast time appears to pass on Mercury from our perspective here on Earth. For the special relativity component, I compare the movement of Earth and Mercury from a static reference point. Then use the Lorentz transform equation to scale the passage of time based on their relative velocity. You can see that you get a periodic variation in the length of a second on Mercury as a function of how the planets are moving relative to each other. But this isn't the whole story. Because of the effects of gravity, the path of light is subtly curved in the presence of massive objects like the Earth, Mercury, and the Sun. The more massive the object, the slower a clock will run. Earth has a higher mass than Mercury does, but it's much farther away from the Sun, so its total gravitational potential is much lower. In systems with much more massive objects like black holes, you have to resort to some complicated numerical methods to really work out the true curvature. But in weak gravitational fields like those around Earth and Mercury, it's fairly common to just add the potential from the planet and the Sun directly, since you get almost the same result, which is what I did in my calculations. We apply our weak field approximation and see that the time dilation due to gravity on Earth is much less than it is on Mercury. For each day, we can calculate the difference in gravitational potential between the two to come up with the time dilation factor given the current positions. Now, we can combine our time dilation due to velocity with our time dilation due to gravity to get the actual relative rates of our two clocks, and plot the cumulative time loss from these fluctuations in our clock speed. As that clock slows down, you can make out how big of a final time difference we have between Mercury and Earth. Converting back to UTC and assuming we've adjusted the time we see in our telescope to account for how long it took the light to travel to us, by November 1st, 2025, our clock on Mercury reads 1 hour, 55 minutes, and 52 seconds earlier than our clock on Earth. That's basically the runtime of Back to the Future. To us Earthlings, there are 2 hours on Mercury that literally haven't happened yet. And Mercury's time slip is nothing compared to the one on the Sun. The Sun's gravity slows time so dramatically that a clock placed there at our starting time would read more than 5 days earlier than our clock on Earth today. It loses about 3 milliseconds in the time it takes to play this video at normal speed. In fact, if you're much more than 24 years old and your entire life had unfolded on the surface of the Sun, from our perspective here on Earth, you haven't even started watching this video yet. I hope you found this interesting. Until next time, I'm analyzing everything.